Hi, I'm Fernando Pereira from UFMG in Brazil, and today we continue our class about tainted flow analysis. We shall see how to implement a sparse version of this analysis. We want a sparse version because it's more efficient than the dense implementation of the tainted flow analysis. The dense implementation suffers from lots of redundancies. For instance, instructions like branches are bound to identity transfer functions. They do not create new information, so what comes in is what goes out. To implement the sparse analysis, you might remember that I mentioned that there are two notions of tainted flow paths that we could use. The first was a path within the CFG, which we had explored in the last class. Do you remember the other kind of paths that I was talking about? These are paths formed by the transitive dependencies in a program. For instance, in this program we have that variable v uses the contents of array get. Thus there is a path from get to v, and x is defined by an operation that uses v, so there is a path from v to x. These are called data dependencies. Now comes the main observation that enables us to implement a sparse analysis. If the abstract state of a variable is always the same, regardless of where the variable is alive, we can just associate that state with the name of the variable, instead of having to associate different states with the variable at different program points. But how can we ensure that the abstract state of a variable, that is, clean or tainted, is always the same everywhere where the variable is alive? Well, we ensure the single information property via live range splitting. First of all, we need to ensure that every variable defined in the program has a single name. That's because the way the variable is defined determines if it's clean or tainted. We can ensure this property by converting the program to SSA form. And if you remember, in a SSA form program, we might have different live ranges reaching the same location. For instance, if we rename x to x1 at L1 and to x6 at L5, what is x at L4? Would you like to think about it? These collisions are the reason why we have 5 functions in the program. So we add 5 functions to the program to merge the live range of variables. We can also learn new information at validators. For instance, at L2 we have a validator, and we know that v will be clean at L3, and it will be tainted at L9. So let's divide v's live range. We will have two new definitions of v. The first is called v2, and it will be valid from L3 onwards. The other will be called v3, and it will be valid from L9 onwards. Notice that v3 is never used, but we create it nevertheless, due to the validator. We also have two definitions of variable v in the program. By now you should know what to do about them. So after renaming all the definitions of variables and creating new definitions at validator points and at join points with the 5 functions, we have this new version of the program. Would you like to think about what's the complexity of creating this kind of representation? We have a 3-step algorithm to convert a program to that representation. We can call it Extended-SSA form, because variables are also renamed at validators. I will let you go back to this slide to understand the complexity of the transformation. For now, we can just accept that we can convert any program to Extended-SSA form in time proportional to the number of variables in the program. That's not the worst case complexity, it's rather the expected complexity. Now that we have a good representation, we shall convert this program in Extended-SSA form into a graph. We will use this table. Don't worry, we will see some examples. So for definitions that are assignments from source, we have this kind of red nodes on the right here, with the circle fitting the variable name. Filters give us the rhombus, like in here. Validators give us the red pattern on the right. All those variables and symbols like the rhombus were created with this validator here. Assignments to sync gives us the pattern with the filled dot that you can see in the red on the right side of the figure right here. And simple assignments gives us the other arrows in the graph, like so. Now that we have this graph, the tainted flow problem becomes much easier. It's actually pretty beautiful. We want to know if it's possible to find a path from the open circle to the filled circle that does not go across a rhombus. For instance, let's start with the assignment from D0. There is a rhombus right on the side and we stop the search. So this part of the program, reachable from D0, is bug-free. Let's look into the definition of X6 now. From X6 we have this path through X5 that reaches a sync, and that indicates a bug. The same bug that we had found with the dense analysis, but much simpler to spot. In this example, the data flow analysis becomes graph reachability because our lattice of clean tainted values has height too. So in practice, it's like if we are propagating information tainted through the graph. Everything that's touched by tainted becomes tainted too. This pattern of traversing and marking creates slices in the program. A slice is the region of the program that's touched by the traversal. If the traversal is forward, then we talk about a forward slice. If it's backward, then we talk about a backward slice. To report a bug, we can take the intersections of two slices. The first, right here, is the forward slice from the bad source to the sensitive sink. The other is the backward slice from the vulnerable sink until this bad source. You can see this intersection right here. The intersection gives us all the paths that from source to sink that are buggy, that can propagate bad information to the sink. Something very important that we have not discussed is that this analysis, to be effective, must be coupled with pointer analysis. Without pointer analysis, we cannot know how information flows through memory. And once we consider the results of the pointer analysis, we can augment the graph with nodes that represent memory locations. But the principle to solve tainted flow analysis remains the same. We have to find paths within the graph. And with this last observation, we close this class on tainted flow analysis. Most of the developments in this class I took from the paper Tainted Flow Analysis on the SSA Forum Programs, which was published in the International Conference on Compiler Construction in 2011. Thank you.